Physics chapter 20, theory video 5. Now we are coming to a little bit more complex calculations. So you have to, because these things are going to be really new for you, you have to pay really good attention, and if you don't understand, please raise questions. So here we have been dealing with we deal with macroscopic properties, that is the properties that do not require us to go into that connects the uh, microscopic models to give out some measurable values, for example pressure, volume and temperature. So they can be readily measured in a laboratory, and then we get an equation PV upon T, which is going to be a constant. So this equation is defined as an empirical relationship. That is, it can be obtained, it can be found out by experimentation. It gives us an idea how it gives us an idea about different situations, but this empirical equation doesn't explain why gases would behave like that, right? So then we have to go into other microscopic details about this. So we know that a gas is made up of particles just like anything else, atoms and molecules, and the pressure rises as a result of the collisions of these particles with the walls of the container. If the collisions are more frequent or faster or harder collisions, that would result in a greater pressure. So then the temperature gives us an idea about the average kinetic energy of the particles. The faster they move, the greater is the average kinetic energy. As a result, higher is the temperature, right? So that is a combination that we have already learned. Then the kinetic theory of gases, it deals with these microscopic properties of particles to the macroscopic. It connects or shows the relationship and tells us why gases behaves the way they behave, right? So then this table this table will explain what are the assumptions that uh, we have taken to develop this kinetic theory of gases, right? Then on the basis of these assumptions, we use Newtonian mechanics. Because this is related to movement and energy, we use that to show that pressure is inversely proportional to volume, that is Boyle's law. Then volume is directly proportional to Kelvin scale, that is Charles' law. So like that we can prove that these relationships exist because of these ideas. Then the theory shows that the particles of a gas have a range of speeds, right? So that means even though the temperature is, in a gas, even though the temperature is constant throughout the gas, still there would be particles that move faster than the others, right? So that means some of the particles would have most of the particles would have the average or close to average kinetic energy that gives rise to that particular temperature. But there can be particles which would have a higher temperature, meaning it would have a higher kinetic energy, and also there would be particles with lower kinetic energy. So all of these taken in average will give a average kinetic energy that results in the temperature that we take. So these are the assumptions and the explanations. A gas contains a large number of particles, atoms or molecules moving at random that collide elastically with the walls and with each other. So when you mention these elastic collisions, you need to remember what elastic collisions mean. So the explanation is kinetic energy cannot be lost. The internal energy of the gas is the total kinetic energy of the particle. So this is an assumption. The assumption is explained in this manner, right? So you might feel that there might be some loss of energy, but still that is the reason why we assume these things to be this way. So the kinetic energy is not lost. The internal energy is the total kinetic energy of the particles, right? So as a result, we can prove, we can assume that it is made up of large particles, and they move at random elastically with the walls and with each other. Then the forces between particles are negligible except during collisions. That is another assumption that we take in proving the Boyle's law and Charles' law. Once again, let me remind you, if you feel confused, we are talking about ideal gases. So ideal gases are different from real gases, right? So these are theoretical assumptions that we make. If the particles attracted each other strongly over long distances, this is the explanation, they would all tend to clump together in the middle of the container. So if they, you know that if there is a, if they, you know, if you put a bunch of magnets close to each other, they will actually clump together. They will come close together. But that doesn't happen, right? So as a result, the forces are negligible except during collisions, right? Other than that, they will just randomly bounce about. Then the volume of the particles is negligible compared to the volume occupied by the gas, right? When a liquid boils and becomes a gas, these particles move farther and farther apart, right? So they are very much farther apart. So that is the explanation for the volume of the particles being negligible compared to the volume of the gas. Then the time of collision by a particle with the container walls is negligible compared with the time between collisions. So these molecules, the explanation is might be a little bit confusing for you to understand. The molecules can be considered to be hard spheres. So these are like, you know, these molecules, you can assume that they are like pool or the carom discs or pool balls, pool of the game of pool. When you hit the white ball, it would go and strike another ball, but that the time it takes for a collision is quite negligible, right? So that is another assumption that we need to make. Just the same thing would happen in carom as well. It hits and then the energy is transferred, and that is a very quick thing, and the time of collision is quite negligible. So this theory was actually very important in in understanding how matter behaves the way it does, right? So this is something that has been developed over a long period of time, and many physicists have been helped by this theory to understand how the world and the system works, how everything works. So now I think it would be best if we can write a note on this, write down the kinetic model, modeling gases. Write down PV upon T is a constant. This empirical relationship does not explain why gases behave the way they do. The kinetic theory of gases that was developed explained based on some assumptions the connection between these macroscopic properties and microscopic characteristics. I think it would be best if you can write down this table 20.1. That would give you a better understanding. Please pause the video and uh, write down this chart. Once you have done that, let's go to molecules in a box. So now we use this kinetic model to get an equation that relates the macroscopic properties, that the pressure, volume, to microscopic properties of the molecules, mass and speed. Right? What we do is we take a single molecule in a cube shaped box of side L. So this is an assumption and a theoretical measurement. So this is what we are reaching to. We take only one molecule. Then we consider the molecule to have a mass m and it is speeding with speed c. Please do not confuse this with the speed of light, because we are going to get equation mc that does not deal with the speed of light. Okay, speed c parallel to one side of the box, right? It rattles back and forth, colliding at regular intervals with the ends of the box. So that means they are it gets bounced back and forth from each wall, contributing to the pressure of the gas. Right? So if we find out the pressure created by one molecule, then we can find out the total pressure by multiplying that by the number of molecules. Right? So this is the relationship that we are trying to prove. So now, as you can see here, there is a single molecule that is moving inside a box of one side length, and it is colliding and it has a speed of c. So these are the equations that we have to familiarize ourselves, and which should be used in this one. Force equals change in momentum divided by time taken, F equals delta mv upon t. Then pressure equals force upon area, then you can use that connection also here, P equals F upon A. Right? So then we should be able to derive the final equation yourself, and that is something that they are going to check at the examination. If you when you go through the past papers, you would understand how it is done. You need to read through the proof carefully, as you will need to be able to derive the final equation yourself. Right? So this final equation needs to be derived, and that is the deriving at the final equation is one thing that they are going to question you on. The stages involved in this calculation are find the change in momentum as a single molecule hits a wall at 90 degrees. Right? Then calculate the number of collisions per second by the molecule on a wall. Right? So these 5 things we have to take into consideration to find out the details of whatever, to find the relationship. Then you find the change in momentum per second, find the pressure on the wall. Then we consider the effect of having 3 directions in which the molecule can move. Right? So then we can figure out, when we go through this proof, you can actually see where each stage is going to start and where it is going to stop. So now we take a single collision, and that collision strikes the side A, B, C, D of the cube. So that means it strikes this side. This side. Right? All right. So it rebounds elastically in the opposite direction. So the velocity is negative c, because it comes in this direction. As you can see, it comes in this direction, and then it goes back in this direction. If this is positive c, then this has to be negative c. I hope you understood. Right. Then so the momentum change it changes from mc to minus mc. So then we how do we find the change in momentum? mc minus mc, the final momentum, minus initial momentum, minus mc plus minus plus mc, that gives us minus 2mc. I hope you understood that, right? Final momentum minus initial momentum. Now so that is what we found. Change in momentum as a single molecule hits a wall at 90 degrees, we found that number 1, right? Then between consecutive collisions with side A, B, C, D, the molecule travels a distance of 2L at speed c. So then here calculate the number of collisions per second by the molecule on a wall, right? So between consecutive collisions with side A, B, C, D, so it goes 2L at speed c. Why does it go 2L? Because one side is L. One side is L, so if for it to collide twice, it has to go back and forth. So if it collides, it goes and comes back. So that is 2L. Now, then and also it goes at a speed of c. Then we can find out speed equals distance upon time. Therefore, time equals this equation. Time equals distance upon speed. So we have 2L upon c, that gives us the time. And now we have find the answer. We can find the answer. Calculate the number of collisions per second by the molecule on a wall. Right? Then we go to C3, find the change in momentum per second. Then now what we do is we can find the force that one molecule exerts on side A, B, C, D. Then we use Newton's second law of motion. I hope you can remember. Force produced is equal to the rate of change of momentum. Change in momentum divided by time taken. So now we found the change in momentum 2mc, that divided by 2L upon c, that gives us the force equals mc squared upon L. The reason why we use plus 2mc is because we are considering the force of the molecule on side A, B, C, D, right? Which is going to be in the opposite direction to the change in momentum of the molecule, right? So that means the reason is, now originally the change in momentum was negative 2mc. But why do we take it as positive? Because we take from this ABCD side, right? From the ABCD, from the opposing side, that is. That is not very important even if you didn't understand that. But remember, change in momentum is taken from the side of ABCD, therefore it is going to be positive. Then area of side ABCD is L squared. We know that one side is L. Then we have pressure equals force upon area. Then mc squared divided by L divided by L squared. Then that gives us mc squared upon L cube. So that is the pressure for one molecule. Then there are large number of molecules in the box, and they all have a different velocity. Each of these things contribute to the pressure. So then we take the average value of c squared, right? So average value of c squared is written inside this kind of in this manner, right? And then we multiply that by n to find the total pressure. N is the number of molecules. Then we get an equation. P equals nm average of c squared divided by L cube, right? So this assumption that we make here is that all molecules are traveling in the same direction and they collide with the same pair of opposite faces of the cube, right? That is, like the opposite sides of a carom board. but they actually move in all directions, then all three dimensions equally, right? Then if we take the three dimensions are x-axis, y-axis and z-axis, then if there are components cx, cy and cz, then velocity in the x, y, z directions are going to be, right? So that means forward, backwards, or the three dimensions, right? Then c squared is going to be sum of these things, cx squared plus cy squared and cz squared, right? So then we can take it as 1/3 of whatever. So 1 cx squared can be taken as, so we assume that they are equally traveling in all directions. So then we can take one of these components to be 1/3 of c squared. I hope you understand that. So cx squared is equal to, in x-axis it is equal to cy, in y direction and z direction. So because all of these are equal, cx squared is equal to 1/3 of the average of c squared. Then for one particular direction, the equation for pressure that we found earlier is the summary. Then if you want to take the component in x direction, and if c is the actual speed, we can take it to be 1/3 of that, or we divide the final answer by 3, right? 1/3 into nm c squared upon L cube. So L cube is equal to the volume of the cube, because length into breadth into height is volume. So that is all are L, therefore it is L cube is volume. Then we can take P equals 1 upon 3 nm, instead of V we put, instead of L cube we put V, into average of C squared. Then we can take, we turn the other way around, PV equals 1 upon 3 nm C squared, right? So that is the final equation that we reach at. So this proof is something that they might ask you to do. So you should be able to do that. So I suppose you understood. If you have any difficulties, please ask me. You should be able to reach this equation in the end. Right. So the pressure of an ideal gas can be found in as part of two equations. P equals 1 upon 3 nm upon V, then average C squared, or PV equals 1 upon 3 nm C squared average. So nm is the mass of all molecules of the gas, and it is equal to the mass capital M of the gas, right? So nm upon V is equal to the density rho of a gas. Then we write P equals 1 upon 3 rho average of C squared, right? So that means the pressure of a gas will depend on the density and mean square of the or the speed of the molecules. That is what we need to understand. Now we need to figure out whether this is a plausible, or whether this is an equation that can be taken to be real or practical. Now to find out whether it really makes sense, we need to understand the different principles behind it. Now we know that the pressure is proportional to the number of molecules, directly proportional. That is, if the number of molecules is higher, then obviously the pressure is also higher. More molecules means more collisions. As a result, there is a greater pressure. So if there is a greater mass of each molecule, there will be more force created in a collision. As a result, it would have more force and more pressure. So that is true in this sense. Then equation gives us that P is proportional to the average value of the speed squared, right? P, pressure, is proportional to the average value of the speed squared. So what that means is, if a molecule is moving faster, it will not only collide at a higher force, but also it will actually collide more often than something that is moving slower. So as a result, that also increases the pressure. Then P is inversely proportional to the volume occupied by the gas. That is Boyle's law. That is, we have deduced Boyle's law. Now, if we take the kinetic model, if the same amount of mass is in a larger volume against a smaller volume, we know that the frequency of collisions would be higher in the smaller volume. So as a result, we know that the pressure is going to be inversely proportional to volume. That is, the higher the volume, lower is the pressure. So therefore, we know that this is a plausible equation. However, this does not prove the equation. These are just theories that we understand through the equation. I hope you understood. If you did not, please ask me questions. This is a little bit of a tricky part. So let's write down the note, and after that we will see how difficult or easy it is. You attempt the questions, and if you are able to do the questions, then all right. If not, please ask me questions. Write down. To obtain a plausible equation for the macroscopic and microscopic relationship of a gas, we consider a single molecule of mass m traveling at a speed of c, simple c, inside a box of side L. We use following key equations to reach the final equation, and then please write down these equations. Force equals change in momentum divided by time taken, that is F equals delta mv upon T, sorry. Then pressure equals force over area, P equals F upon A. Write down. Before you write down, please draw this 20.8. Pause the video and draw it. Once you have done it, write down. Even if you need the 5 steps involved, you might want to write this down as well. That is proving the equation. After that, write down. When a single collision on ABCD side and subsequent collision of the same of the molecule is considered, we can obtain the change in momentum as follows. I hope you can remember. So because it collides uh, in on the wall in this direction, it is c. Then it when it rebounds, it is negative c, right? So because of that, the change in momentum is going to be final momentum is minus mc divided minus mc minus plus mc, the original or the initial momentum. Change in momentum equals minus mc minus plus mc. Minus mc minus mc gives you minus 2 mc. Between consecutive collisions with side A, B, C, D, molecule travels a distance of 2L at speed c. Hence, time between collisions with side A, B, C, D equals 2L upon c. Using the force equation, we can apply Newton's second law of motion. Force equals change in momentum divided by time taken. So the change in momentum is 2 mc. As you can remember, earlier we discussed, because we are taking in the opposite direction from A, B, C, D. That is opposite direction in the change of momentum of the molecule. Then 2 mc divided by 2L divided by c. Then from that we get mc squared upon L. Applying this to pressure equation, pressure equals force over area mc squared upon L divided by L squared, which gives you mc squared upon L cube. This is for a single molecule. When taken for all the molecules N, with different velocity, different molecules with different velocities, C should be the average of all the velocities, and it is written as, write it like this. So the pressure equals, now we multiply mc squared upon L cube by capital N, that is the number of molecules, to find the total pressure. P equals capital N m, then the average of c squared divided by L cube. Now you know about 3 dimensions. So the in all 3 directions it would have components. This equation, leave a line and write, this equations suggests that all molecules are moving in one direction, but in reality they all move in all three dimensions. That is x, y, and z. As a result, we can take the average of velocity in one dimension to be 1/3 of c squared. Please write this part, that is c squared equals cx2 plus cy2 plus cz squared, and from that you can get the equation from that because this is equal, then you write this equation and then you can get this equation. I hope that makes sense to you. Then leave a line and write, because L cube is equal to volume, we can write, after you write this equation, then write this one. Right? This is the most important equation. Please put it inside a box or something and mark it as special. The quantity Nm is mass of all molecules, which is capital M, and also because Nm upon V is density, we can obtain the equation P equals 1 upon 3 rho average c squared. Please read through this plausible, the proving part once again and see whether you can understand. If there is any doubt, please ask me. You have to pay attention to these five points and proving those 5 points, and using all of those details in an equation is another important factor that you need to remember. I will give you a note on this how plausible it is part as well. Write down. This equation is plausible because, number one, pressure is proportional to the number of molecules. That is, P is proportional to N. P is proportional to N. This is proportional, not infinite. Number two, more molecules mean greater pressure. Number three, greater mass creates greater force during collision. Next point, P is proportional to the average proportional to C average C squared, that put the put this um, this one, write down, because when a molecule moves faster, two quantities will actually affect it. Not only it strikes the wall harder, also it would collide more often. Also it would collide more often. Next point. P is inversely proportional to the volume within brackets Boyle's law because when the volume increases, frequency of collisions reduce. Also, it shows us that the pressure becomes lower while being inversely proportional to volume. I hope you understood. If you have any questions, please ask them. If you understood, please attempt to do question number 13, 14.